How are you, my students? My name is Naftal Lucas Makumbile from Premier Girls Secondary School. I'm teaching chemistry. Today, I want to present the lesson that is just the continuation of the lesson that we started in the last lesson. And the topic that we are going on to discuss is energetics, and the subtopic is Hess'S law. My dear student, this topic is related with the Form 3 topics, that is chemical kinetics, equilibrium, and energetics. So this is just the advanced knowledge on how to deal with that topic. Now, my dear student, today specifically, I'm going to present to you the determination of enthalpy change for the chemical reaction using Born-Haber cycle. By the end of this lesson, I am sure you'll be able to utilize principles, concepts, and skills in doing various activities in chemistry, even practicals, and also to use chemical equation, formula, and symbols to communicate in chemistry. But you can ask yourself, my dear student, why this presentation? Why Born-Haber cycle? Some of the students are getting some challenges on how to draw the Born-Haber cycle and even to calculate the enthalpy of formation or lattice energies. Why are they getting these challenges? Because some of the students, they get problems on how to differentiate between dissociation energy and atomization energy in the Born-Haber cycle. I'm sure, my dear students, today, the lesson that you are going to discuss together will help you and make you to be confident and competent when dealing with these problems. So you are warmly welcome. So let's stay together till the end of this lesson. Now, my dear students, as I said, we are going to discuss about Born-Haber cycle. Now, when we talk about Born-Haber cycle, my dear student, what comes first in your mind when you hear the word Born-Haber cycle? I hope that in your class, you studied about it. So today, I'm just giving you some skills on how to deal with different problems relating to Born-Haber cycle. Now, when we discuss about Born-Haber cycle, if I ask you, what is Born-Haber cycle? I am sure that, my dear student, you will be able to tell you the definition. What is it all about? Born-Haber cycle, in short, is a thermochemical cycle which represents all the steps of reaction and the mechanism of the formation of the compound. So it is just application of the Hess'S law to the enthalpy formation of the compound. The Born-Haber cycle will enable us to understand and to calculate the enthalpy formation and the lattice energies of different ionic solids at 25 degrees of Celsius. So, my dear students, the Born-Haber cycle will enable you to solve different problems. But before you draw the Born-Haber cycle, there are very important things for you to remember. There are arrows. Before we go to the examples, I want to give some skills. What are the arrows which are indicating that cycle represents? Now, we have this arrow. The arrow which is pointing upward, this represents endothermic process. So the arrow which is pointing outward represents the endothermic process. And the one which is pointing downward So when you see the arrow pointing downward, that means that process is exothermic. And when the arrow is pointing upward, that means that process is endothermic. My dear student, I'm sure that you know. Now, to remind you, when you talk about exothermic process, this is the process which involves the release of heat or energy to the surrounding. When you talk about endothermic process, this is the process which involves absorption of heat from the surrounding. So these two processes are very important when you want to draw the Born-Haber cycle. Now from there are different ways of constructing the Born-Haber cycle. But today I'm going to present one of the simplest ways on how to draw the Born-Haber cycle. Now let's see the examples. We have the first example. There are different ways of asking these questions using the Born-Haber cycle. And this is one of the ways when the questions about this particular part might come. The first one, the first example, draw the Born-Haber cycle for aluminum oxide. That is the question. It is one of the ways of asking these questions. Now, my dear students, the question says, draw the Born-Haber cycle for aluminum oxide. What are you required to do? Or what are you going to do with that question? The first thing, before you think to draw the Born-Haber cycle, you have to know how to write the chemical formula. The chemical formula, this is a very simple one because you have studied in ordinary level, in Form 2, in the topic of chemical formula, bonding and nomenclature. So I'm sure that that is not a problem. Is it true, my dear students? Yes. Now, if you are going to fail to draw the to write the chemical formula of the given compound, it will be very difficult for you to solve the problem given or to draw the Born-Haber cycle. So it is very important to use the symbols and the formula to write the correct chemical formula of that compound. So the compound given there is aluminum oxide. The compound is aluminum oxide. What is the chemical formula of aluminum oxide? It is made up of two elements, aluminum and oxygen. The formula is this one. That is the formula. Now, in that formula, so if you have already written the formula, what to do? What is the next step? Now you started drawing the Born-Haber cycle. Now, let's be together on how to draw the Born-Haber cycle in a simplest way. So what you have to do, you have to write that compound, aluminum oxide, at the bottom here. This is ionic solid. Then you underline, you put the line here. This is the compound. This compound is formed from two elements, as you can see. How many elements? I mean, there are two elements. What are those elements, my dear students? You can see there is aluminum element and there is oxygen element. Sorry, my dear students. So we have aluminum and we have oxygen. But when we talk about enthalpy formation, the formation of a compound, that means the elements which make that compound should be in the pure standard state. The pure standard state of aluminum is solid because it is a metal. The pure standard state of oxygen is a gas, a diatomic molecule, because it is a non-metal. So you write these elements at the top of this one. The arrow will point downward. Why? Because the enthalpy, the information of aluminum oxide is exothermic process. That's why the arrow is pointing downward. So we write the elements which make this compound here. This is aluminum. You write solid here. And followed by oxygen gas. Oxygen gas. Those are the two elements. Now from there you balance the equation, because these are reactant and this is the product. It is very important for you to balance. If you don't balance, you are going to get the trouble when you are going to make some calculation. So it is important for you to balance the equation. When you balance, here we have 2 aluminum, so you put 2 aluminum here. And the oxygen, here we have 3 gaseous atom of oxygen, and here we have 2. What you are going to do, you put 3/2 there. So the equation is balanced. So what is the name of this one? We can write because this is the enthalpy of formation. It is not good to write the whole words here, but we can use the symbols. We can say the enthalpy of formation. That means that is the enthalpy of formation of this compound. Now, after we have given the elements which make this compound and the compound as well, the next step, because there you have the metal and the non-metal. Now, this is the ionic compound. You have to get the cation and the anion. The cation from the metal, that is aluminum, and the anion from the non-metal, that is oxygen. Therefore, from there, how cation is formed? Aluminum metal forms the cation by losing electrons. How many electrons are lost? How many electrons are lost from aluminum? Maximally, 3 electrons are lost from aluminum in order for the aluminum to acquire the noble gas stable structure. I'm sure that you have studied this one, my dear student, and I hope that we are together and remember it. So here, before we go to the ionization process, we have to convert the solid aluminum metal into gaseous form. Now here, the conversion, it is purely endothermic process. So aluminum, we have 2 So that is the conversion. Aluminum solid is converted into aluminum gas. That process, what is the name of that process? Hope, my dear students, are together. What is the name of that process? That is sublimation. So this is sublimation. Enthalpy, sublimation. We write in short there. It will not be proper to write the whole words there. So we write in summary. Now, this is aluminum. 2 moles of aluminum gaseous atom. And here we have 3/2 moles of oxygen gas. So after we have sublimated or atomized aluminum, now the next step is to ionize the aluminum metal. Now, because I said that aluminum will lose 3 electrons, losing 3 electrons is a stepwise process. 3 electrons can't lost at once. No. One after another. So we have the first ionization energy. That means the first electron is removed from a gaseous aluminum atom. We have the second ionization energy. That means the second electron is removed from a gaseous aluminum ion. We have the third ionization energy. That means the third electron is removed from a aluminum dipositive ion. Now, this is the first ionization energy in summary. But remember that we have balanced it. For example, if you sublimate 2 aluminum solids will be submitted into 2 moles of gaseous aluminum. So here you have to multiply it by 2 because there are 2 moles of aluminum. Also, when you are ionizing, also you multiply by 2. You multiply by 2. It is important. Some of the students, they are ignoring that or they forget. So if you forget, if you'll be asked to find one of the enthalpy in the steps involved in formation of aluminum oxide, you're going to get wrong. It is important for you to multiply this one because the number of moles which are indicated there, they're very important to be involved. Now from there we go to that is the first one. This is the second ionization energy times 2. 2 times second ionization energy. We go to the third one. This is the third ionization energy times 2. And the arrow is pointing outward for the all ionization energies. Why? Because removing electron from the gaseous atom or gaseous ion is purely endothermic process. That means energy is used to remove an electron. It is not easy. Remember, each atom has got the nuclear attractive force, which is at the center of an atom. So nuclear attractive force is holding the electron towards it. So removing an electron needs energy to take the electron from the shell of each atom. So that's why the 3 ionization process are purely endothermic process. So we have formed the cation already, aluminium 3. So what next? We have completed with the cation. Now we go to form an ion. In order to form an ion, here we have oxygen gas. It is a molecule. A molecule is unreactive. So we have to convert the unreactive form of that molecule into the active form. That is an atom. An atom is the active part of an element. So we convert that one. So the conversion of a molecule into gaseous atom, that is atomization. So we atomize oxygen gas. Now remember, these 2 will cancel. 2 and 2 will cancel. So you're going to remain with 3 there. With 3 there. Remember, the number that is here should also be present here. It is important for you to remember. If you miss here, if you are told to calculate anything, you're going to miss everything. So it is important. The number which is present on the atoms which are present at the compound should also be present at this particular point. So this is atomization energy. Atomization energy in short. But there are 3 gaseous atoms of oxygen. So here you multiply by 3 because there are 3 there. So we have atomized oxygen. Now we have the atom. The atom is the active part. Is the one which gains electron for the case, because this is non-metal. In order to make an ion is a negative charged particle. So because oxygen is a non-metal, it gains electron. How many electrons can be gained by oxygen atom, my dear student? I'm sure that you know. In order for the oxygen atom to acquire the noble gas stable structure, it must acquire, or it must gain 2 electrons. So we go to ionization process. Now, the first electron, when it is added to a gaseous atom of oxygen, that process is purely exothermic process. So the arrow will go downward. Here you have aluminium. That one. So this is electron affinity. That is electron affinity. Now from there, because there are 3 atoms of oxygen, you multiply by 3. You multiply by 3. So that is the first electron affinity. It is always exothermic process. Now from there, we have completed that one. It is not yet, because oxygen receives maximum 2 electrons in order to form a stable ionic structure. Now from there, the gaining of the second electron or second electron affinity is always endothermic process. So the arrow will point upward. The arrow will point upward this way. So from there you write, here you have aluminium, 3 ion, 2, this is the gas, plus 3 oxygen. Sorry, my dear students. Here you have 3 oxygen, 3 oxide ion. Sorry. So this is an ion. Now from there we have already the cation and an ion. And this is the second electron affinity. You multiply by 3 because there are 3, sorry to write this one, first electron affinity. Now, from there, because we have obtained the cations, these will combine to form this ionic compound. So when these ions, cation and an ion, combine together to form this ionic solid compound, the energy which is released is called lattice energy. And it is purely ectothermic process. So this is the Born-Haber cycle for the formation of aluminum oxide. So it is very, very important for you to draw this one. Now from here, you can formulate an question or the formula to find whatever will be asked. Because I told you at the beginning that Born-Haber cycle is the application of the Hess's law. How are you going to apply the Hess's law, my dear students? How can we apply the Hess's law from this Born-Haber cycle? When you want to get the enthalpy formation, for example, of aluminum oxide, what are you going to do? It is simple. I'm sure that even yourself, the right where you can be able to tell. When you want to get the enthalpy formation of this compound, we just sum the enthalpy of formation of all the steps involved in this particular process of forming aluminum oxide. So this is a very simple way of drawing the Born-Haber cycle. It is very important for you to remember each step and multiplying the number of moles for each particular step because they will be used in the calculation. Are we together, my dear students? So that is one of the ways the questions might come. So you can meet with this question even in your national examination. So it is important. From there, we can go to the second example. Now, my dear students, welcome to the second example. The second example is here. Second example says, using the Born-Haber cycle, determine the lattice energy of magnesium chloride given the following data. The first data, the enthalpy of formation of magnesium chloride is negative 876.3 kilojoules per mole. The second one, atomization energy of magnesium metal is positive 54.8 kilojoules per mole. You have the first ionization energy of magnesium is positive 502 kilojoules per mole. You have the second ionization of magnesium is positive 1005 kilojoules per mole. Atomization energy of chlorine molecule equals to positive 138 kilojoules per mole. Electron affinity of chlorine is equal to negative 286.5 kilojoules per mole. So, my dear student, that is the second way these questions relating to Born-Haber cycle might come. So, when you are asked such kind of example, what are you going to do? It is very simple to solve those problems. It is very simple. Now, when you ask those questions, do not rush to solve the problem. Try to think what first is required. Now, before you make any calculation, the skills of this problem, first you have to draw the Born-Haber cycle. That is very important. Because the Born-Haber cycle will lead you to calculate the enthalpy, the lattice energy. If you rush to solve the given problem, you might end up getting wrong answers. Because in the given equation, you might use one of the data, which is not required. But the Born-Haber cycle will give you the correct steps of solving or finding the lattice energy. So let's go together to solve that problem on the board. The formula, we have first to write the formula of the compound. The compound is magnesium chloride. How do you write the formula of magnesium chloride, my dear students? I'm sure that there you are. You have written it. Now, let's write together here. This is magnesium chloride. This is magnesium chloride. This is ionic solid. Now, my dear students, after you have written the correct formula of magnesium chloride, as the question requires, now you go to draw the Born-Haber cycle. When you draw the Born-Haber cycle, in the simplest, you write here at the bottom, that formula of the compound, magnesium chloride. This is ionic solid. You draw the line at the bottom here. When you do that one, you have to identify the elements that have been used to make that compound. And when you look at this compound, there are two elements there. We have magnesium and we have chlorine. Now from there, at the top of it, because the enthalpy of formation of this compound is exothermic, that's why the arrow is pointing downward. So at the top of this one, you write the symbol for each element that has been used to make this compound. But the symbols of these elements should be in their pure standard states, as I said. So magnesium solid, because it is a metal, plus chlorine. The pure standard state of this element is a gas, the atomic molecule. So this is the gas. From there, you balance. You have to balance the equation because this is the product and this is the reactant. Magnesium is 1, magnesium is 1. So there is no problem with magnesium. Chlorine, there are two atoms of chlorine. It is also balanced. So we write in summary here, this is the enthalpy of formation of magnesium chloride. After we have written the elements which make that compound, what follows? That means you have to get the cation and the anion from the given elements. Now each one has got the process. For example, when you want to get the cation, magnesium from the cation. But first you have to convert it from solid state into gaseous state for it to lose electron easily. So the conversion of solid into gaseous, that is sublimation. We start with magnesium. This is magnesium. The enthalpy of sublimation of magnesium. So conversion of solid magnesium into gaseous magnesium atom. So from there, as I told you, we start with the metal. When we finish with the metal, we go to the non-metal. So what follows is the ionization process. How many electrons are lost by magnesium? I'm sure that you can tell me the maximum number of electrons that a magnesium element can lose in order to acquire the stable noble gas configuration. I'm sure that you can be able to tell. 2 electrons maximally can be lost. Now, losing 2 electrons, it is a stepwise. So the first one, this is the first ionization energy. That means 1 electron is lost from 1 mole of a gaseous atom of magnesium. From there, the second electron is also lost. This is the second ionization energy of magnesium. That means 1 electron is removed from 1 mole of a gaseous magnesium ion. So we have completed with magnesium, and we have already the cation, which is magnesium ion. Now we go to the chlorine. Chlorine there is a molecule. A molecule is the unreactive. So we can't because a nanometal gains electron, it can't just gain electron in the molecule form. No, it has to be converted into the active part of it. the active form of it, which is an atom. So conversion of chlorine molecule into a gaseous atom, that is atomization. But here, because there are two chlorine atoms, now here we are going to get 2 moles of gaseous chlorine atoms. So here we are going to have 2 magnesium ion plus 2 chlorine gaseous atom. Now, my dear student, there is a challenge to some of the students because they fail to differentiate. What is it? Is it an atomization or dissociation? Remember, in atomization, when you study it in a class, atomization, 1 mole of gaseous atom is formed from a molecule. But in dissociation, 2 moles of gaseous atoms are formed from a molecule. So when you look here, there are 2 moles of chlorine gas which are formed. So automatically, this is dissociation energy, not atomization. If you write atomization here, that means you have to multiply by 2 because 2 atoms of gaseous chlorine are formed. So it is important for you to remember. Now from there, we have atomized the chlorine atoms. Now we have to form an ion. This chlorine atom, because it is a nanometal, it gains electron. But how many electrons can be gained by a chlorine atom? It is only 1 for it to acquire the stable noble gas configuration structure. So gaining 1 electron is purely ectothermic process. That's why the arrow points downward. Now, this process of gaining electron is electron affinity. Electron affinity. Energy released when 1 mole of a gas gains an electron. Now, here remember, there are 2 moles of chloride ions, not 1. If you forget to multiply with this number here, you're going to get wrong results. So you multiply by 2. It is important for you to know that one. Now, my dear student, here we have already obtained the cation and an ion. These 2 will combine to form the solid magnesium chloride. So this one will combine to form magnesium chloride, and this is lattice energy. Lattice energy. So lattice energy is the energy released when 1 mole of ionic compound is formed from its ion. So this is the Born-Haber cycle. This Born-Haber cycle will guide us in order to solve the required problem. Remember here, we are required to determine the lattice energy of magnesium chloride. So, my dear students, from this Born-Haber cycle, we can formulate the formula here. Application of the Hess's law. Entropy of formation of magnesium chloride is the summation of all entropy changes of all the steps involved in forming ionic magnesium chloride solid. So here we formulate the formula here, that entropy of formation will be equals to, we sum this one. We have entropy of sublimation plus, we got the second one, first ionization energy. We go to the second one, second ionization energy. Second ionization energy. We go to the third one, dissociation energy. Dissociation energy. We go to another one, electron affinity times 2. It is important to remember. Electron affinity times 2. Then we finish with the last one, lattice energy. That is the formula to use. What are you required to find? The lattice energy. But before you do anything, the question comes, do you have all the data as given? Yes, we have the data. They are already there. Now, because they are already there, now we have to analyze some of the issues. One, when you talk about the dissociation energy, is the dissociation energy given in this question? No, there is no dissociation energy there. But we can obtain dissociation energy. How can you obtain dissociation energy, my dear students? This is where some of the students are failing. That's why I told you, before you make any calculation, you have to draw the Born-Haber cycle. In the given equation, you are given the atomization energy of chlorine. But in the Born-Haber cycle, which is the correct way of solving this problem, dissociation energy is needed. So you have to follow the Born-Haber cycle. Now, my dear student, how to determine the dissociation energy? Let's determine this one. Dissociation energy, as I told you, is equal to 2 times atomization energy. 2 times atomization energy. Now, because we have the data there, we can just multiply to get so that we can substitute all these values into the given formula. So dissociation energy will be equal to 2 times the given value for atomization energy of chlorine molecule is this one, positive 138 kilojoules per mole. So you multiply by 138 kilojoules per mole. My dear student, you just use your calculator. I'm sure that you have the calculator. Hope you're following this program. Now, when you take your calculator, you take 2 times 138, you're going to get 276. So dissociation energy will be equal to 276 kilojoules per mole. That is number one. Another thing that we're given, electron affinity. Electron affinity given is only for 1 mole, but here there are 2 moles. That's why I told you it is important for you to multiply. So we just also analyze that one in order to simplify our calculation. So electron affinity will be equal to 2 because there are 2 moles of chloride ions there. You multiply by the given value, which is negative 286.5 kilojoules per mole. When you use your calculator to find that one, 2 times negative 286, you are going to get electron affinity will be equals to negative 572 kilojoules per mole. So that is a simple way to analyze the data given. From there now, because we are looking for lattice energy, you can make it the subject. You can make it the subject. How do you make the subject? That means the enthalpy of formation you minus with the summation of all these in the from the right-hand sides. So here, the enthalpy of formation minus bracket, take this one, enthalpy of sublimation plus first ionization energy as given here plus second ionization energy plus dissociation energy plus electron affinity, this one, equals to lattice energy. Now, because you have the data here, my dear students, you have the data here. The enthalpy of formation is negative 876.3 minus, in bracket, sublimation energy, you are given there positive 54.8 kilojoules per mole. First ionization energy 502 plus second ionization energy 1005 kilojoules per mole plus dissociation energy you have already calculated here. It is 276 plus electron affinity you have already so calculated here is negative 572 kilojoules per mole is equal to lattice energy. So my dear student, you can use it is very simple calculation. You can use the calculator. First you have to deal with the bracket there. Let's sum together. Now, my dear students, after making that calculation, you are going to get negative 2,142.1 kilojoules per mole. This equals to lattice energy. So the lattice energy of magnesium chloride equals to 2,142.1 kilojoules per mole. So that is a very simple calculation that you can make. It is important for you to remember the techniques which are used here, multiplying this one and also determination of this one. Remember, in the question we are given the atomization energy, but in the Born-Haber cycle, the dissociation energy is required. So it is important for you to remember that one. I hope, my dear students, we are together. That is the second way when these questions might come. From there, my dear students, we can go to the third example. Now, my dear student, we have the third example there. The third example says, why the second electron affinity is endothermic? That is the process, that is the question. My dear student, that is also another way when this question might come. If you are given that question, what are you going to solve it? How are you going to answer that question? It is a very simple one. It doesn't need a calculation. It's just the explanation. My dear students, as I told you, that the second electron affinity is endothermic, and even in the Born-Haber cycle, we drew the arrows were pointing upward in the two Born-Haber cycle that we drew in this lesson today. Now, I told you that it is endothermic process. Why is it endothermic process? Because the first added electron, which makes the first electron affinity, will create repulsion. Because remember, electron is negatively charged. So when it is added to the valence shell of an atom, it creates repulsion. So when the second electron is added, repulsion will be created because negative charge and negative will repel each other. Now what will happen there? Energy must be used to add the second electron. So it is endothermic process because energy is required to overcome the repulsion caused by the first added electron. That's why it is endothermic process. So that is a very simple. I'm sure that, my dear student, you can be able to answer that question. So it is very simple, that one. Now, my dear student, when you go to the to another example, we have another example here. My dear students, another example here is the lattice energy of calcium chloride is given negative 760 kilojoules per mole. And that of calcium chloride is negative 2,184 kilojoules per mole. Which compound or crystal is stable than the other? Give a reason for your answer. Now, my dear student, that is another way. Sometimes you can be asked to compare the stability of the given compound by using lattice energy. Not only lattice energy that can be used to compare the stabilities of the compound, but also the enthalpy formation can be used. Now, because the question is asking about the stability of the compound using the lattice energy, let's deal with this one, and then I will give you a brief about the second part. When you are given the compound, that one you are given, in this example 4, you are given calcium 1 chloride. The enthalpy is negative 760 kilojoules per mole. The second one is calcium 2 chloride, is negative 2,184 kilojoules per mole. When you are given these questions, you have to compare the energies which are given out, because the process of forming this compound are purely exothermic process, because their values are given in negative. The enthalpy changes are given negative, so they are exothermic. always highly ectothermic compound, which are indicated by more negative enthalpy formation, are highly stable, because when a large amount is given out to form a solid ionic compound, that means that compound is very stable. So when you compare the two compounds, calcium 2 chloride is formed with a large amount of energy released by forming this ionic compound. So this calcium 2 chloride will be stable as compared to calcium 1 chloride, because a large amount of energy is released when forming this compound. So it is very simple when you are dealing with these problems. So calcium chloride is more stable. The reason is that it is highly ectothermic compound, because it is formed by a large amount of energy released, so it is energetically favorable. But also you can be asked when you are given the lattice energies, one is negative value and the other one is positive. That means we have ectothermic compound and endothermic compound. Which one is stable? Always ectothermic compound are stable compounds. Now also we can be given two endothermic compounds. That means both values have positive values. Now which compound will be stable than the other? When you meet with such kind of question, the one which is less endothermic, that means with less positive, will be more stable. The one with highly positive or highly endothermic will be less unstable. So my dear student, these are different ways of asking this question. And this topic is applied in our daily life. For example, respiration process. We are taking food. The food is digested. The end product of digestion is absorbed into the cells. Oxidation of the end product of digestion in the cells. Energy is released. That energy which is released enables us to do our activities. We are going to the farm, we are studying, we are doing activities. That is one of the real application of this topic. But also, for example, cars, moving cars, machines, in industries, wherever, burning combustion of the fuels in the engines, which enables the car to move, or the engines to operate, the machines to be operated. So the burning of combustion is another application of this important topic. But also, my dear student, even at home, you are cooking the food. Using what? You are using fuel. What fuel are you using at home? Charcoal. Burning of charcoal releases energy, heat energy. That heat energy you are using to cook the food. If you are using the gas as well, energy is given to the food. So this topic is applied in our daily life. It is very real applied in our daily life. Now, my dear student, today's discussion is very important for you. First, to memorize the terms that are used in energetics as you study in the introductory part. But also it is important, before you make any calculation relating to this particular part, it is important to draw the Born-Haber cycle. The Born-Haber cycle will guide you on how to draw that one. But also, my dear student, application of the Hess'S law is the summation. When you want to find the enthalpy formation of the compound, you sum all the enthalpy changes of all the steps that are used to make that ionic solid compound. So it is important for you to remember that one. Now, my dear students, I want to take this opportunity to thank you, because I'm sure that today you will be confident to solve different problems relating to this particular part. So I would like to take this opportunity to thank you, because we are together. I'm sure that and I hope that we are together. Thank you very much. Let me welcome to the next session, and the next lesson will be, we are going to look at another topic, that is organic chemistry, particularly on the properties of carbonyl compound. Thank you very much for this time. Have a good time.